So you said something kind of when you were explaining how you got interested in volcanoes and how you got your career, that the ocean crust is built by volcanoes, which I started to learn when I was reading some of your research. And it makes total sense to me, but it's also, I mean, I guess when you are in school, you're kind of just taught like tectonic plates and things shifting around. So how does that all kind of work together?
Yeah, so quite a lot of the Earth is built by volcanoes. Not all of it. So the continents that we sit on, I mean, also in a lot of cases built by volcanoes, but a different kind. But the oceanic crust, which underlies most of the big oceans, that's all built by mid-ocean ridges, so volcanic eruptions at mid-ocean ridges. And that happens where the tectonic plates are moving apart. So the Earth is broken up into sort of the crust of the Earth is broken up into lots of different plates and they move around and interact with each other. So sometimes they rub alongside each other, like in San Andreas, and they can produce big earthquakes. And in other places, one gets forced underneath another one, and then you get sort of arcs like the Pacific Ring of Fire, where you get lots of very explosive volcanoes. And then in other places, they move apart from each other, and there you get what we call mid-ocean ridges, and that's where you get this crust constructed. And there is one down the middle of the Atlantic, the Mid-Atlantic Ridge, but there's also some in sort of all of the other oceans pretty much that you can think of. In those locations where the plates move apart from each other, they overlie the Earth's mantle. And as you get moving apart of the plates, you reduce the pressure on the mantle. And often when you take the pressure off something, it will melt. So if something's under high pressure, it's harder for it to melt because it can't get bigger. But if you reduce the pressure, if the conditions are right, then it will melt. And that's exactly what happens at mid-ocean ridges. So you get melting of the mantle. And then those melts erupt on the seafloor, usually in like a couple of thousands of meters of water. So yeah, they're pretty cool.
Yeah. So what does that look like? I mean, we picture volcanoes on land and it's usually some kind of like mountainous looking structure and lots of molten magma, red hot spewing everywhere. But you put that in the water, does that look the same?
It depends on the water and it depends on the volcano. At mid-ocean ridges, we get a quite diverse selection of different types of volcanoes. We still get red hot lava coming out, but because there's lots of pressure, it's harder for gases in it to exsolve. So by exsolve, I mean come out as bubbles. Most eruptions are driven, especially explosive ones, are driven by bubbles of water or carbon dioxide or sulfur dioxide a bit that are dissolved in that sort of magma before it erupts. But if you've got still lots of water pressure, that's much harder for it to happen. So the lava comes out and it erupts on the seafloor, but usually not very explosively. And then because it's coming into contact with water rather than air, it cools really quickly as well. So you get this like crust form on the outside really, really quickly. And it tends to form, like normally what happens in a relatively sort of calm eruption is you form pillow lavas. And they're like sort of like big round bulbous lava forms. And they're very beautiful. And they all connect together and they form a lot of different types of sort of seafloor, what we'd call geomorphology, so different seafloor landforms, really. And some of them are really interesting and we don't even understand how they form currently, and others we've got a better idea. The most common sort of hummocky cones, so they're just like little individual volcanic cones, and they usually only erupt once, so they don't have like multiple eruptions like we'd expect from a big on land volcano. They just sort of erupt once and then that's it, there they are, they've cooled down and that's it. Usually a single eruption will form more than one of those. So you'll get like an eruption along a fissure and then you'll get multiple cones that form along it. Then we also get these things called flat top seamounts. And they're really interesting because they're big round volcanoes. They're about a kilometre across. And then they're completely flat on top. And normally when something's flat on top, it's because it's been above the sea. But at mid-ocean ridges, this has never happened. So they've never been exposed above the sea. It's not an erosional surface. People don't really fully understand yet how those form, so why they have this flat top and why they look like that. And then if you have very, very high effusion rates, if you have a really big eruption, so that tends to happen more where you've got plates moving apart from each other faster. There you tend to get big run-out lava flows because the lava's coming out so quickly, even though that crust is forming quite fast. The lava breaks through it the whole time, and then you tend to form these sort of big, smooth run-out lava flows on the seafloor as well. So yeah, it's really diverse down there, and the interplay between all of those different types of volcanic systems is really complicated. And there's lots of unknowns still about it. For example, we don't really know how far magmas will travel sort of along a ridge and erupt. We don't know if they're all localized or maybe they can be transported tens of kilometers and erupt somewhere else. So yeah, lots of questions.
Yeah, this is so fascinating. So you're finding that, I mean, they all kind of erupt along the same fissure, and it can be just different types of volcanoes that are creating these different magmas, but more or less along the same tectonic plates.
Yeah, so different ridges are spreading at different rates. So we tend to separate mid-ocean ridges into slow, intermediate, and fast spreading. And the mantle has variation within it, so like compositional variation within it for all different kinds of reasons. But usually at a mid-ocean ridge, it's relatively simple melts. We tend to call it mid-ocean ridge basalt or MORB. And it's used as sort of like a standard to compare other lavas to, because people joke about how boring it is. Like when we go on a cruise and I collect loads of basalts and I'm excited, everybody else says they're very dull, which is rude. But so it's usually compositionally quite simple. We do see variations in the composition, but not big variations. And it's usually a pretty pure mantle melt that you get. And the landforms that are produced primarily depend on how big the sort of amount of magma being erupted was and how quickly it came out. So fusion rate is really important in sort of defining what kind of landforms you get. And that varies between slow, intermediate, and fast spreading ridges. So at slow spreading ridges, we don't really think that we get magma chambers in the same way. So normally when we picture sort of a classic volcano, it's got like this chamber underneath it of molten magma that's like ready to erupt at any point. That's not super realistic anyway, but it's the way that most people would sort of envision a volcanic system. But at slow spreading ridges, the crust is so cold that you can't maintain a sort of big chamber of melt long term. So they're quite ephemeral, the magma chambers. They come and go, they freeze quite quickly. And so you get small eruptions quite far dispersed in time. So you tend to get pillow lavas and like hummocky flows there. Whereas where the plates are moving much faster, you've got a higher temperature gradient there. So the crust underneath them's a bit hotter. It's a bit easier to maintain melt. We usually have pretty steady state magma chambers, in inverted commas, underneath them. And so you get larger volume, faster run out eruptions. So compositionally, they're slightly different, but also the effusion rate there is very different, which means that the landforms you produce look quite different.
And landforms meaning, the type of crust that's formed?
Yeah. So again, compositionally, in terms of like the chemistry of the actual lavas that are coming out, not hugely different. There are some differences.
So it's more of a structure and what it looks like.
Exactly, yeah. Structurally, they can be quite variable. And that's interesting too, because you often form sort of like thicker, colder volcanic crust close to a slow spreading ridge than you do a fast spreading one.
This is so fascinating. So what is the most common? Like, do slow spreading ones and like the pillowy sort of byproduct, or the more fast moving ones?
They're both common, but there's more slow spreading ridges as a sort of length of the mid-ocean ridge system than there are super fast ones. But it's a whole diversity. You get ultra slow spreading ridges as well. And they're super interesting because if you get spreading that's really, really slow, and we see this in places on slow spreading ridges as well, but if you have really, really slow spreading, you don't melt anything. So because the movement is so slow and the crust is so cold, you hardly get any melting of the mantle underneath at all. And what happens there is that when the plates move apart, instead of erupting lavas, you get these sort of very deep faults. So faults are like cracks in the crust where things can sort of move past each other. So like brittle fractures really with movement on. And you can get those that become really deep rooted. And instead of getting volcanic eruptions, what happens is you keep extending and keep extending, keep stretching the crust there. And eventually you start to expose mantle rocks on the seafloor. So in really, really slow settings where you have hardly any volcanic material, you'll get seafloor like that. So you get a full spectrum from that through to thick, higher fusion rate volcanic piles, all produced by the same tectonic process, but just at different rates.